So let's talk about the subatomic particles. So atoms are the building blocks of elements, but atoms actually have particles inside of them. All atoms are composed of the same subatomic particles. Subatomic just meaning smaller than the atom. And the three major subatomic particles are protons, neutrons, and electrons. So protons and neutrons have nearly identical masses. And for the purposes of Chem 1A, we can think of them as being the same size. Okay, they're very, very slightly different. Here's the mass of the proton, the mass of the neutron. Using that number might come up in a homework problem or a worksheet problem. It's not a number you need to memorize. Okay. The mass of the electron is significantly smaller. Okay. Here's an illustration. If the proton had the mass of a baseball, an electron would have the mass of a rice grain. So that gives you an idea of the relative sizes of protons and electrons. Electrons are really small, almost 2,000 times smaller than protons and neutrons. So those units here, kilograms. Kilogram isn't a good unit for expressing the mass of a neutron because we end up with this crazy small number. And even if we used grams or nanograms, we'd still have a very small number. And so we need a different unit for expressing masses that are that small. And the unit we use is very creatively called the atomic mass unit. The abbreviation is AMU. So atomic mass unit is for measuring the masses of atomic-sized particles, atoms. So 1 AMU is defined as 1/12 the mass of a carbon atom containing 12 protons and 12 neutrons. It's kind of an odd definition. What it ends up being is that a proton or a neutron has a mass very close to 1 atomic mass unit. And that's something we should remember. Protons and neutrons have a mass of approximately 1 atomic mass unit. Some of these particles have charges. The proton has a positive charge. So the relative charge compared to the electron is +1. The electron has a negative charge. The charges on those two particles are equal in magnitude. They're the same size. They're just opposite in charge. So one's positive and one's negative. So when we get an electron and a proton together, they don't have any charge because the charges add up to 0. The neutron has no charge. So protons are positive, neutrons are neutral, and the electrons are negative. These are the actual masses in kilograms. These are the masses in atomic mass units. So what do you need to know out of this? Well, for the mass, I'd like you to know that that one's approximately 1, this one's approximately 1, and this one's approximately 0. So we should know that. We should know the relative charges. Here are the actual charges in coulombs, and it's great that we know that, but we don't have to memorize that, okay? Proton, +1 charge, 1 atomic mass unit. Neutron, 0 charge, 1 atomic mass unit. Electron, -1 charge, approximately 0 atomic mass units. Okay? So matter is generally charge neutral because the number of protons and electrons that are present in the substance are equal. And so then there's no overall charge. Sometimes, though, we do get an imbalance in charge where we get the protons and the electrons separated. And when you get a charge imbalance like that, it usually stabilizes or equalizes very quickly and often dramatically. An example of this is lightning. So lightning can be loud and scary and bright. And so what happens here is we've got a negative charge that builds up on the clouds, a positive charge building up on the ground, and lightning is the equalization of those charges. Very dramatic. Static electric shocks are also equalization of charge imbalance. So we don't get that so much here because even in the winter, the air is not super dry. In the Midwest, where it gets really cold and you run the heaters, it gets very dry. And so you shuffle your feet wearing socks on the carpet, and then you touch something metal and it sparks. The last time my parents live in Minnesota, and I remember being at home, and the room was completely dark. There wasn't a nightlight or anything. And I was rolling over in bed, and I'm like, am I seeing things? It's like there were like fairies or something in the room. There's these little flashes of light. And I was like, I'm a scientist, so I'm investigating this, trying to figure out what it is. And I finally realized it was static electricity of just me rolling over in the bed. All these little flashes of light, you could see them. It was really kind of trippy. But that's the equalization of a charge imbalance. Any questions? So elements are defined by the number of protons that they have. So protons are found in the nucleus. Protons and neutrons are both found in the nucleus. And it's the number of protons that defines what element that atom belongs to. So the number of protons is called the atomic number, and it's given the symbol Z. That's from the German word Zahl, meaning number. Personally, if we were doing this from English, we'd probably call the atomic number A, but it's from the German. So it's Z. Number of protons. So helium. Here's a helium balloon. Each of those helium atoms has, in its nucleus, 2 protons, because that's what makes it helium. The graphite in your pencil lead contains carbon. Every carbon atom has 6 protons. Okay? That's what identifies that atom as being carbon. It's got 6 protons. So on the periodic table, which is a list of all the known elements, it's got kind of a funky shape. We'll learn more about why it is that shape. But we have the elements listed in order of their atomic number. So it goes from left to right, 1, and then it jumps over here to 2, 3, 4, etc. In each of the boxes, there is an element symbol, capital first letter, lowercase second letter, and above that symbol is a whole number, an integer, 1, 2, 3, 4, etc. That is the atomic number, the number of protons in the nucleus of that atom. On this periodic table, the name of the element is also listed, but on the periodic table on the wall, the ones you're going to have for exams, the name is not listed. That's why you need to memorize them. It takes way too much time to always be looking for the name. So each element is identified by a unique atomic number and a unique chemical symbol. Now, you've already memorized a bunch of these. I think I gave you about 35 of them, the most common ones. Those chemical symbols are either 1 or 2 letters, and they're listed on the periodic table. The first letter is always capitalized. The second letter, if there is one, is never capitalized. And we have to be really consistent in that so that we understand what the other person is saying. So helium has the symbol He. Carbon is capital C. Many of those symbols are based on the English names. He for helium, well, that makes sense. It's the first 2 letters of the word helium. Carbon is the first, C is the first letter. But some of them don't seem to make sense, and that's because they're from the Latin or sometimes even the Greek names. So sodium. Sodium has the symbol Na. That doesn't seem to make any sense because there isn't an N or an A in the word sodium. So where does that come from? It comes from the original Latin name for sodium, which was natrium. It's the first 2 letters of the Latin name. So some of them are a little weird. I'm sorry, but we just have to deal with it. So all atoms of a given element have the same number of protons, the atomic number. They do not necessarily have the same number of neutrons. The neutrons contribute mass to the atom, but they do not affect the charge. So if we've got different atoms that have the same number of protons, they belong to the same element, but if they have different neutrons from each other, they're called isotopes. Iso is a prefix meaning the same. So these are part of the same element, but they're a little different, right? So they're variations. As an example, all neon atoms contain 10 protons. But some of them have 10 neutrons, some have 11 neutrons, some have 12 neutrons. You can't tell how many neutrons it has just looking at the periodic table. That has to be determined experimentally. So all three of these neon isotopes exist. They each have a slightly different mass because the mass of the atom is very close to the sum of the mass of the protons and the neutrons. The relative amounts of each different isotope is roughly constant no matter where you get your sample. So if you get a sample of neon from North America and one from the South Pole and one from Eastern Europe, and you look at the distribution of the isotopes, it's going to be very close to the same distribution. But we can't say that, well, there's three isotopes. That must be that 1/3 is this one, and 1/3 is that, and 1/3 is that. They are what they are, and we just identify what they are. And so it might be, 95 and 5, or it could be anything. And so that's just been experimentally determined. So when we add up the number of neutrons and the number of protons in an atom, that gives us the mass number. It's the number of massive particles. The electrons are so small that we can just kind of ignore them in terms of mass. But the mass number, we count up how many neutrons and protons there are. That's given the symbol A. I would prefer A to be for atomic number, but they didn't ask me. So A is for mass number, Z is for atomic number. Is that confusing? Yeah, I'm sorry. So atomic number is Z, not this. See, it started. A is the mass number. It's the number of protons plus the number of neutrons. And so we can represent the different isotopes for an element in a couple of ways. One is with what I call a nuclear symbol. So here's the chemical symbol from the periodic table. And to the left, we have a superscript and a subscript. The subscript is the atomic number. The superscript is the mass number. So those three isotopes of neon would be symbolized like this. So they all have the same atomic number. They all have that subscript of 10 on the left. But the superscript is different because the superscript is the sum of the protons and the neutrons. What's a little bit convenient about this is if you go like this and subtract the lower number from the upper number, 20 minus 10 is 10, and that gives you the number of neutrons. So this is the number of protons. This is the combined neutrons and protons, and if you subtract, you get the number of neutrons. Another way to indicate the different isotopes is to use the chemical symbol and a dash followed by the mass number. We don't really need to specify the atomic number because the atomic number is available on the periodic table. And you should just assume that anytime you're doing anything with chemistry, that you would have a periodic table accessible. So we don't need the mass number to be specified. So then we could call this Ne20, or we can use the full element name, neon 20. So this is the neon 20. It has 10 protons and 10 neutrons. This one has 11 neutrons, and that one has 12 neutrons. Any questions? So here's a table just summarizing those three isotopes of neon. Here's symbols, ways we can represent them. They all have the same number of protons because they're all neon. The number of neutrons is different, and thus the mass number is different. Here's the natural abundance expressed as a percentage. So 90.48% of all neon is neon 20. That's the most common isotope. Only 0.27% is neon 21, and 9.25% is neon 22. These are not numbers that you would memorize. Okay, those would be given if needed. Any questions? So let's do some practice here. So what are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? And I put a periodic table here. So the carbon isotope, we have to find carbon on the periodic table. So that's the symbol C. So this is carbon. How many protons does a carbon atom have? 6. It's that number right above the element symbol. So the number of protons is the atomic number. So the atomic number, given the symbol Z, for this carbon isotope is 6. There's 6 protons. What is the mass number for this specified carbon isotope?
13.
It's 13. It's going to be the number of neutrons plus the number of protons. They told us how many neutrons because we could not find that on the periodic table. So 7 plus 6 is 13. And so the mass number, A, is 13. And then the symbol. There are 3 different ways we could represent that carbon isotope. So we could put it like this, carbon with a 6 down here and a 13 up there. That's one style. We could call this C13, or we could call it carbon 13. So in answering these questions, I would accept any one of these 3 as the symbol. But so you don't have to give all 3 of them since it doesn't ask, but you should know what all 3 of these notations mean. Any questions? How many protons and neutrons are present in an atom of this? I'd read that, potassium 39. Well, how many protons? 19. We actually don't even have to look at the periodic table for this. This is the atomic number, the number of protons. So it's got 19 protons. And how many neutrons? 20. We just take these numbers and subtract them. So 39 minus 19 is 20. So it's got 19 protons and 20 neutrons. Any questions? So the number of protons is always the same for all atoms of a given element. The number of neutrons can vary. So what about the electrons? Well, if we have a neutral atom, that means we must have an equal number of positive and negative charges. So the number of electrons in a neutral atom has to be equal to the number of protons. So that's the same as the atomic number. So an atom of carbon, its element number 6. It has 6 protons. How many electrons does it have? 6. Same number. Atoms can gain or lose electrons, though. They're not going to change their protons and neutrons in a chemical reaction, but the electrons can be lost and gained. So if you lose or gain electrons, you're going to have a charge on the particle now, and then we call it an ion. An ion is an atom that has a charge on it. So we can have positively charged atoms, such as Na+. Those are called cations. So a cation is a positive ion. We can have negatively charged ions. F-, those are anions. So you need to remember that cation is positive, anion is negative. If you like cats, you have positive feelings for cats. Cations are positive. If you don't like cats, I don't know. Maybe look at anions, and this one has an extra N in it. I mean, they both end in N here, but this one has another N. This is the negative one. So come up with a way to remember those. To write the charges of the ions, we write those as superscripts to the right of the element symbol. We always write the sign for an ion charge. But we'll find as we go out throughout the semester that chemists often omit the number 1. So this is a positive 1 charge, but we didn't write the 1. We just wrote the plus. And this is different from how we write exponents in math, right? If you were looking at x to the first power, you would just write x. I mean, you could write x to the 1, but it's really not necessary. But you would never see x to the plus or x to the plus 1. That would be really weird in math, wouldn't it? Those two would be weird. You would write x to the minus 1 if you had a negative power. So when we write these, we always include the sign, and we would write the sign after the number. So those are all 1s, but if we had like calcium, we would write calcium 2+, not calcium +2. And the way I think of this is we don't want this charge to be mistaken for an exponent. We don't want to think, oh, we've got Ca raised to the second power. And so we're writing it different than we do in math.